All right, chapter 8 looks mostly at exponentials. So we've looked at linear, quadratics. We looked at radical functions last chapter, square roots, cube roots. We've looked at polynomial functions like raising to the third power, the fourth power. So this whole chapter focuses on exponential, meaning that the variable will be in the exponent of the equation. So the standard form is y equals a times b to the x power. Just like standard form of a quadratic was ax squared plus bx plus c, this is standard form for an exponential graph. So that's what it tells you here. It's a function with a general form. They just write a bx. It's understood multiplication. A cannot be 0. B has to be greater than 0. And b cannot also equal 1 because it would not be exponential. So there are two types. There are exponential growth, where it will increase, what they say, exponentially. It gets larger very fast. Or you can have exponential decay, where it starts out large and then it minimizes. So for growth, the b factor will be greater than 0, or greater than 1, excuse me. And for the decay, the b value will be less than 1, but I should probably say greater than 0. So let's say between 0 and 1. So it'll be like a fraction, 1/2, 1/3, 2/3. All right, so they ask us to graph each of these. Obviously, if you're using your graphing calculator, you can go to your y equals and type it in and just graph. I'd like us to do it by hand first, and then we will use the calculator to verify our results. So this is 2 to the x power. So, of course, creating a table of values, we would just plug in. Normally, you'll get to pick whatever numbers you want to plug in. But we'll do this without a calculator. So I'd have 2 to the negative third, 2 to the negative second, 2 to the negative first, 2 to the 0, 2 to the first, 2 to the second, and 2 to the third. And then we'll evaluate those again without the use of our calculator. What is 2 to the negative third? What do we do with negative exponents? Move it to the denominator. So this would become 1 over 2 to the positive third. 2 to the positive third is 8, so this would be 1/8. So the ordered pair would be -3, 1/8. That's one of my ordered pairs. And then just keep going through. This would be 1 over 2 squared, which would be 1/4. This would be 1 over 2 to the positive 1, which is just 1/2. Anything to the 0 power is what? 1. And then the rest of them are easy. 1, 2, 2, 4, and 3, 8. Now, sometimes when you're graphing these, when you do your table of values, you might get really large numbers, which means you may have to scale your axes. Now in this one, if you're looking at my x values, they all fit between -10 and +10, and these also fit. But on your homework, you may have to scale this, like count by 10s, count by 5s, and you can just write it like off to the side, so that way it doesn't like get lost in your graph. You also could have to change the x-axis, and then you just go plot your points. So -3, and again, it's going to be hard to graph 1, but try. And then we are going to connect the dots with a curve. Now you'll notice that the exponential function up here, it looks like it might go down. It will never go underneath the x-axis. So it's going to get very small, like close to 0, but it's going to never actually touch 0. So the graph, when you connect these dots, you do not want to draw it going underneath the x-axis. It's just going to get like really close to it. And that's because when you take a positive number and raise it to an exponent, it never becomes negative. No matter what you plug in for x, you would never get a negative answer for y. You would get a fraction, a really, really small fraction, like 2 to the -100th, would be 1 over 2 to the 100th, which would be a very, very small fraction, close to 0, but not 0 itself. Now the next one, they add in this a value in front. So you have to use your order of operations. You have to do your exponents first and then your multiplication. So for the first one, why don't you guys try this one on your own? I'll show the first one and then you guys can try filling out the table. We'd have 4 times 2 to the negative third power, which would be 4 times 1 over 2 to the third power, which would be 4 over 8, which then reduces to be 1/2. See if you guys can complete the rest of the chart, and then you will need to scale your axes to fit all of these numbers on there. So you'll have to scale, and you'll notice that this one is a little bit more skewed. Should look something like that. So they call them exponential functions because obviously the variable's in the exponent, but also the numbers increase exponentially, like really fast. The biggest place that we'll see this is population growth. Population growth is said to be exponential because as soon as you have a few people, they can procreate and have more people, and so they grow at an exponential rate. So that's what the majority of the word problems will be about in this unit, is population growth in cities based on a certain year. They'll give us a growth rate, and we'll be able to write an equation and model the scenario. So again, you want to think about the general form equation, a times b to the x. When you're reading the word problems, the variables will stand for specific things. So this is going to model population growth. So A is said to be the initial population. Initial meaning the starting population before we have any growth occurring. B is said to be the growth factor. Which is how much the population is increasing. Now there's a formula to calculate growth, because if I tell you that it's increasing at a rate of 1.24, you can multiply by changing that to a decimal, 0.0124, but then you would have to add it back to show growth. So there's a formula for the growth factor, and that is B equals 1 plus R. R is the rate of increase. Or decrease, technically. That would just be a negative number then. But rate of increase, and we'll put as a decimal. So you'll have to convert the percent to a decimal first, and then plug it into that formula. So an example, see, 3, they say refer to the graph below, and this is the U.S. population from 1800 to 2000, and they tell us in 2000 the annual rate of increase in the U.S. population was about 1.24. So this is your R value. The rate is 1.24. We do want to change that to a decimal, so I'm going to change that to be 0.0124. You move the decimal 2 spaces to the left or divide by 100. Suppose the rate of increase continues to be at 1.24. Write a function that models the U.S. population growth in millions after the year 2000. So we'll go to the year 2000, and you can see that the U.S. population was 281 million, okay, but we'll just leave it 281 so we don't have to put out all those decimals. So a function has to be an equation. It could be y equals, f of x equals, whatever. A times b to the x. Remembering that A is our initial population. So the initial population is not 5, because we're starting at 2000 and we're using that to move forward. So because it says after 2000, we'll use that as our initial population, 281 times the growth factor, which we have to find the growth factor. Again, the formula is 1, which is like 100% if the population were to stay the same, plus the increase rate. So we'll plug that in, and we'll get 1.0124. Basically, you just add a 1 in front of the decimal. But that's including the 100% of the population that's already there and adding that growth to it. So this will be 1.0124 to the x power. So that's our function. Now you do have to define your variable. So x, and it tells us up here somewhere, x is the years after the initial population. So x would equal the number of years after 2000. You do have to define the variable because the variable will be different for every scenario depending on what year you started. So make sure that you do define the variable. Part B asks us to predict the U.S. population in the year 2015 to the nearest million. So 2015 would be 15 years after the year 2000. So we're just going to plug in 15 for x into our function. We will use our calculator for this. You'll just use your caret button to get your exponent of 15. And they say to the nearest million, so approximately 338 million. Million people. Yes. Next one, similar type of problem. We don't have the graph this time, but they do ask us some different questions, and I just want to make sure you understand what is being asked of you. The population in the U.S. in 1994 was about 260 million, so that's your initial population. What variable is the initial population, A, B, or X? Abby? A. With an average annual rate of increase of about 0.7. So R would be 0.007. Make sure you move the decimal appropriately. Part A says find the growth factor. What variable is the growth factor? A, B, or X? Growth factor. Lexi? B. Remember, the formula to find B is 1 plus the increase rate. So that would be 1 plus 0.007, so the growth factor is 1.007. So if they ask you for the growth factor, you're just finding out what B is. Suppose that the rate continues to be 0.7%, write a function. So again, we'll be writing our exponential function, a times b to the x, using our initial population of 260, times b, which we found out was 1.07, excuse me, 1.007, to the x power. And usually I put parentheses around it because it just helps to group that and put it all to the same exponent. Again, we have to define what x is. So x would be the number of years after 1994. So if they asked you to use this to predict something, like say in the year 2015, you would have to take 2015 minus 1994 to figure out what you're plugging in for x. Okay? All right, the last types of problems, we are on the next page for today. We have 2 more. And these are going to be writing exponential equations when given 2 points. Okay, so if it were linear, we would do find the slope, do point slope, get it all into slope-intercept form. But they're not linear, they are exponential. So I have steps typed out here, and we're going to go over those in depth when we go through each one. So you're going to start with your general form, y equals a times b to the x. you'll substitute in x and y from your first point, or your second point, doesn't matter. But you'll take one of the points and you'll plug that in for x and for y. And then you'll solve for a. So when I say solve for a, you're going to get like a equals, like, no, we'll get like b to the second divided by 3 or something. You're not going to get an actual number, you're going to get an expression. And then you'll plug that in for b in the equation, and you'll use your second point until you can find out what a or b are. Okay? So it's kind of like substitution, solving by substitution, a system of equations. All right, so we'll start with our general form. We'll plug in our first point, remembering that this is x and this is y. So 4 goes in for y. 2 goes in for x. So 4 equals a times b to the second. Now we solve this for a. Well, what do I need to do to solve for a? Caleb? Divide by b squared. So we'll get that a equals 4 divided by b squared. So we're going to take that and plug it back in for a to get a new equation. So we'll have y equals, you might want to do parentheses, 4 divided by b squared times b to the x power. What we've done now is we've gotten rid of the a variable. We now only have b, x, and y. Now you'll plug in your second point. Again, for x and for y. You cannot plug them both in at the same time. It has to be into both separate equations. So this will get me 16 equals 4 divided by b squared times b to the third. Now we only have one variable that we don't know, and that's b. We can now solve for b. To do so, we need to simplify the b's and the exponents using our rules of exponents. So this b to the third is really b to the third over 1. So I can multiply the numerators and the denominators together to get 4b cubed over b squared. And we can simplify this. Subtracting the exponents, 3 minus 2, just gets me b to the first. So that's just 4b. Divide by 4, and we'll get that b is 4. Okay, that's part of my answer. The final answer is going to be y equals a times b to the x, plugging those numbers back in. So to find out what a is, go back and plug your b value in. So we'll get 4 over 4 squared, 4 over 16, which we can reduce to be a is 1/4. Now we take both of those and we plug them back into our general form equation, a times b to the x. So we'll have y equals 1/4 times 4 to the x power. See if you guys can try example 6 while I'm passing out your homework, which is a worksheet because you all have graphs. So I gave you graph paper. See if you guys can try number 6. And then I am going to show you how quadratic regressions. There's an exponential regression that we can do. So let's go ahead and use that to check our answers. So if we press our stat button, edit. Okay, you got to clear out whatever you have in there for your lists. If you arrow up to the top and hit clear, not delete, you can clear those out. And then you would just type in your 2 points, L1 being x and L2 being y. So 1 and 0 and 6 and 2. So if you want to put this in your notes, stat edit. And then we'll do stat calculate. So pressing our stat button, arrowing over to calculate. And this time we're going to scroll all the way down until we find an exponential regression, which I think is number 0. And remember, you do have to hit enter 2 times. Those of you with the new calculators, you have to go through a couple prompts. But you'll get that A is 2, B is 3, and then you plug those in. Remember, this is just telling us the correlation coefficient, so it's saying it's a perfect fit. It goes exactly through the points instead of saying it's like really a close fit. It's an actual perfect fit. Anyone need help with their calculator? Are we all fine in that? All right, the rest of the time is yours to work on your homework then.